2.8. Today we're going to take a look at 2.8, and 2.8 is called the Mean Value Theorem. And to start with, we're actually going to take a look at, we're going to take a look at another theorem that is a simplified version of the Mean Value Theorem. This is called Rolle's theorem, a mathematician named Rolle. And it says the following: suppose that we have a function that is continuous on the interval AB, and it's differentiable on the open interval AB. And then there's the one other condition here that says that f of A equals f of B. So the end points have the same y value. They're the same height. What this is saying then is that there is a number between A and B where the derivative is 0. So let's pause for a moment and see if you can remember the details. When a derivative is 0, what does it look like? We usually see a maximum or minimum. There are cases where we don't, but those are the ones we've dealt with the most, right? Maximums or minimums. In general, or more specifically, I guess you could say, because then it would cover out cases that are not even that case, is that what do you see about the tangent lines? The slope equals 0. What does the tangent line look like? They're horizontal. We see horizontal tangent lines when this happens. So take a minute and take a look at this picture, and you'll see that a visual of what this is saying. So I'm going to draw you a couple of pictures. Let me draw the first one. We'll draw it like this. We'll call that point A, and we'll call this point B. And if I drew them well, then that should look like that they're the same height. Is that reasonably okay? What this theorem is saying is that there's a location between A and B where I have a horizontal tangent line. And I hope you look at that and you say, well, of course there is. Now, it's important to note that the details of how this happens are really important. You have to have 3 things true in order to make this actually work. You have to have a curve that's continuous, right? If the curve had the ability to sort of break into pieces, we wouldn't necessarily have the ability to have that curve at the top where we get that tangent line like that. If this were not differentiable, so let's say instead we had a slope or a curve that looked like that. I'll use the word curve very loosely. This is continuous, right? But this point at the top is a sharp turn, and it's not differentiable there, yeah? I have no derivative there, so I definitely can't say then that the slope there would for sure have to be 0. In fact, it isn't. It's not defined at all, because there's not a derivative there at all. And then we have to have the endpoints that are the same in order for this to happen, right? Obviously, if we had endpoints that went from, well, how about have from A to that particular point? If you just used these 2 points right here, well, there's no slope of 0 between those 2 points, right? I couldn't make this claim because these 2 points don't have the same y value. So those 3 details are really important in order to be able to make this claim. Now, notice it says there is a number that does this. It says A, that is, and you kind of think that they're saying there's one number, but it could be more than one value. Like, let's say, for instance, that the graph looked like this. And we talked about this particular point being A. And if I drew it well, I think that point's at the same height as about B. How many slopes of 0 do you see? 2. We've got a maximum and a minimum in this particular graph. So right here at the top and right here at the bottom, it appears, anyway, visually, that we have a slope of 0 at each of those places. So so we could actually say that there's actually 2 C values, a C1 and a C2, for which it happens in this particular graph. Does that make sense? So this theorem doesn't actually say that there's only one place where this would happen. It just says you could almost say that they're saying there's at least one. There's at least one spot where I've got this slope of 0 going on. All right, so we're going to change gears, and we're talking about the other main theorem in this section. It's the mean value theorem. And it has some of the same conditions at the beginning that this original one had, the Rolle's theorem had. First, you have to have the function continuous. The second thing you have to have is differentiable. So it doesn't have the condition about the endpoints matching, right? But it says there is this number C between A and B. But instead of it being that the slope is 0, it tells you that the slope then of that point, at the point C, is f of B minus f of A over B minus A. What is that equation? We've seen it before. F of B minus f of A over B minus A. Do you recognize it? A little bit different form than I've used it in class, but Do you know what it is? What is f of b? What do we mean when we say f of b? You're talking about the whole thing right here? Yeah, this is a slope on the right-hand side. What is it a slope of? Do you know? That's an equation for slope. You're right. F of b and f of a are y values. That's why we've got the y values on top. And we've got x values on bottom, b minus a, right?
Is it rise over run?
This is rise over run between
2 points.
2 points. So this is the slope between a and b. These are x values, x equals a and x equals b. Let me draw a picture. I think that will help. So we need to have it continuous. It needs to be differentiable, but we don't need the endpoints to match. So let's say for a minute that it looked like this. Same nice, or at least fairly nice curve. If I find f of b minus f of a, what that really finds is that finds the slope of this line. Right? We take this function value, the y value, minus this y value, and we divide it by this x value minus this x value. It's the slope of that line. What this theorem is saying is that there is a location between a and b. It's about like right there probably, where if I did a tangent line, it's not entirely convincing, but you can imagine. If I did the tangent line at that particular point, these two tangent lines would have the same slope. These two lines would have the same slope. The top was the tangent line, this is a secant line. And can you imagine if you took the end of this one right here, and you said, okay, well, let's not stop at this point B, let's stop over here. And you just had a different y value, that this line would just sort of move this direction, you'd have a different c value as well. So there's always the ability to make this happen. Do you remember in class when we talked about something called the intermediate value theorem? You guys had a homework question from the intermediate value theorem where it talked about going up a hill in a car, being a positive velocity, right? You were moving forward, and then you rolled backwards down the hill, so you were going a negative velocity, and you should be able to argue, so to speak, to the officer that, well, at some point in there, your velocity was 0. Do you guys remember that? And we talked about that being the intermediate value theorem. Well, I talked about in class another one that was specifically a mean value theorem problem. It was about the cop saying that even though he didn't clock you going a certain speed, he could figure out the distance you went and actually find out what your average speed was, that stuff. Remember that? That's the mean value theorem. It's an application of the intermediate value theorem, an example. So that's what we're doing on these problems, is we're going to actually be able to talk about finding these particular point C's. So let me show you an example of what we're going to look at. The directions on this one sound like there's a lot going on, and there are quite a few steps. The first thing says to check the hypothesis of Rolle's theorem and the mean value theorem. The hypotheses are almost the same, but you've got to figure out which theorem you're supposed to be using. So if you check all three of those hypotheses from the first theorem, you'll know if you're using the first or the second theorem. And then we're going to find a value of C that makes the conclusion true, and we're going to draw a graph. Okay? So the first thing is to check the hypotheses. There's 3 parts of the hypotheses. What's the first one? Continuous. What's the second one? Differentiable. And what's the third one in Rolle's theorem? Right. Very good. So these are the 3 things that I need to check. Continuous. Is this continuous? Well, I think it is. Why do we know that this is continuous? How do you know? It's a polynomial, and in fact, that's the phrase I want. We actually had a theorem that said that if you have a polynomial, it's continuous everywhere, and it also said it's differentiable everywhere. So the reason that this is continuous and differentiable is because it's a polynomial, and polynomials are always continuous and differentiable. So you almost get those for free. And while that's true, you almost get those for free, you still have to tell me that you checked that, okay? So right here, we checked both of these things, and they're both true. They both work. And the reason is because this is a polynomial. Does that make sense, Zach? Because you're the one that went down the route, yeah. Okay. Now the third one's a little different. That's going to change depending on the problem, but it's actually going to be using whatever the endpoint values are that we have. So we have endpoints of -2 and 2, and what we have to test is we have to test whether or not they actually are the same. So we're going to find what is f of -2 and what is f of 2. So f of -2 means we have -2 squared plus 1, and the other one is +2 squared plus 1. So what is f of -2? That's 5. What is f of +2? 5. So which theorem will this actually be a specific case for? Rolle's, because they match. If we had gotten at the end that one of these was 5 and one of these was 2 or something else, right, then we would be talking about the mean value theorem next. Okay, this statement right here tells us that we're going to be using Rolle's theorem. All right, so Rolle's theorem says what? Well, let's go back and just take a look real quick. Rolle's theorem says that if we have those first conditions, those hypotheses, then there is a number where f prime of c is equal to 0. Well, this is talking about a derivative, so the next thing I'm going to do is I'm going to take a derivative. Does that make sense? What I'm doing is I'm looking for that value of c that actually makes this really work. So let's take this function. And after all of the exciting and fun functions you guys have been doing lately, this one is neither fun nor exciting, is it? It's very simple, right, Shannon? Yes. What's the derivative of x squared plus 1? 2x. And according to Rolle's theorem, I should be able to set this equal to 0 and solve it, and there's going to be a place where that will work. So what in the world value would make that work? 0. Yeah. X equals 0 should make this work. And I'm only asked for the c value, right? I don't actually have to find the x and y coordinate pair. This is just finding, let me go back over here, finding the value c that's between a and b. So I just found the number 0 that's between -2 and +2. Okay? So let me write that down. So f prime of 0 equals 0, and that 0 is between -2 and +2. It asks for a graph as well, so we'll graph this next. You probably know what this graph looks like. I think you should. If you don't, you want to grab your calculator, that's okay. Do you know what this graph looks like? It's a parabola. What's the y-intercept? It's at 1. Yeah, this should look like a parabola, sort of shifted up 1 from the origin. So the basic overall graph looks like this. Let's try one more time. That's a little bit better. And there's the -2 and the +2 that we have as our endpoints. And this location right here is where that slope is 0. All right, that doesn't look very convincing, but I think you guys are agreeing with me that it works, right? Is that okay, Tyler? Yeah, okay. The limitations of my technology sometimes just, all right, it's okay though. All right, so this is the graph that it's talking about, showing that we do in fact have a location where the slope is 0. It is at what we found to be the correct value, which was the x value of 0, which is between -2 and +2. Everybody good with the picture? Makes sense in the problem. Okay, we got another one of these we're going to do. Same directions, different function. Our function is sine x, and our interval is from 0 to pi halves. So we're supposed to take a look at this particular one. Same direction, so the first thing I have to talk about is whether it is continuous and differentiable. All right, so tell me, is it continuous? Is it differentiable? Can you picture what the graph looks like in your mind? Sine graph? It's the one that looks like the wave, right, like this. Any asymptotes? No, not for sine. If this graph were tangent, we'd have problems, right? But this is continuous, and it's differentiable. And actually, just like the last one where we could say, because it's a polynomial, we actually had a theorem that said sine curves and cosine curves are also always continuous and differentiable. So we kind of get this one for free as well. So this is because it's a sine curve. Yeah, because it's a sine curve. Let me say it that way. Now let me pause for a moment because it hasn't come into play, these interval that we're looking at on any of these, because the two functions that I chose to present are continuous everywhere. They're differentiable everywhere, right? But not all functions are, right? All polynomials, all sines and cosine. But what if you had tangent? Tangent is not continuous everywhere, right? But could you make the window small enough that on a piece of it, it was continuous and differentiable? Sure, you just have to avoid the asymptotes, right? So if you looked at the tangent graph and you only looked between negative pi halves and positive pi halves, we'd be good to go as well. Because tangent curves are continuous between negative pi halves and positive pi halves. So that would be an example where the interval you were looking at would determine whether or not it satisfied those conditions. These ones that we did didn't have that problem. Now the third thing we're supposed to do is to test the endpoints, right? F of B equal to F of A, or vice versa. So we need to find out what is F of 0 and what is F of pi halves. So this would be sine of 0 and sine of pi halves. So what is the sine of 0? It is 0. What is the sine of pi halves? Say it, Brooks. It's 1, yes. These don't match, do they? Not like the last one. So which theorem will apply? The mean value theorem. Since these don't match, we're talking about them. So this one fails. We don't have it equal. So we're going to talk about the mean value theorem. Okay, so let's take a look at the mean value theorem. The mean value theorem talked about finding a slope that's equal to f of b minus f of a over b minus a, right? So we actually have to do two parts to do the mean value theorem. We have to do the derivative part, because that's the left-hand side of this. And we have to do the right-hand side of this, which is calculating the slope. I'm going to do the calculating the slope part first. Not really because I have to. We're just going to start there. So we're going to calculate the slope between 0 and pi halves. Okay, so that would be, I'm going to write it out. This is actually finding f of pi halves minus f of 0 over pi halves minus 0. F of pi halves, we just found it was the number 1. F of 0 was the number 0. And this is over then pi halves. So this is the number 1 over pi halves, which we wouldn't leave written that way. What would we do? Flip it, yeah. So this becomes 2 over pi, right? Yeah. So this is the slope, 2 over pi. It's a funny looking slope, I agree. We could find an approximation if we wanted to talk about approximately what is that. But since pi is approximately 3.14, right, this is about 2/3. This is a slope that's about 2/3. All right, so what we're supposed to find, though, is we're supposed to find the c value that makes this work. So we're supposed to find where in the world does f prime of x equal to 2 over pi? Well, we haven't found f prime of x yet, so let's do that. What in the world is f prime of x for the graph? We have the graph of sine x. You guys know this. It's cosine x. And so what we're wanting to do is we're wanting to find out where does cosine of x equal 2 over pi. Because that's what we're supposed to be able to find, right? This theorem says I should be able to find this point where this works. Do you remember, this is the furthest in trig that we have sort of meandered in this calculus class so far. Do you remember how to solve for x when you've got cosine of x equals 2 over pi? Very good. It's the inverse cosine. Depending on where you took trig, you might have also heard it called arc cosine. So we're going to take, and I'll write it in here this way. It's the one that looks like it's got a little -1 exponent, and we're going to do it on both sides. On the left-hand side, when we do the inverse cosine of cosine, we get x. On the right-hand side, we simply get the inverse cosine of 2 over pi. Now, if 2 over pi were a x value on your unit circle, we could actually write this down, right? If this said that, instead of it saying 2 over pi, it just said the number 1/2. That's on my unit circle, we could deal with that. 2 over pi, not on my unit circle. It's not even on my unit circle in terms of angles. But it's definitely not on the unit circle in terms of the x, y pairs of points that you have around the circle, right? So you can get an approximation. In fact, if somebody would for me, just so that we have a reference point when we draw a picture, let's find out approximately what this is. The actual answer is this answer, inverse cosine 2 over pi. That's the exact answer for our problem. And so we're going to use it exactly, but for our graph, we're going to need to talk about it in a little bit more general sense. But we can say so by the mean value theorem. This x value, cosine of 2 over pi, is between, it's on the interval between negative, oh wait, no, it wasn't negative, 0 to pi halves. And f prime of this value, we'll just say f prime of that x value, equals the 2 over pi. What is it approximately?
8806.
Yeah, that's fine. 88 is good. So we're looking at roughly 0.88. Does anybody know, and since you've got your calculators out too, so this is actually the value for the x up there. Does anybody know approximately what the value for 2 over pi is? Not 2 over pi, I'm sorry. Pi over 2 is what I want. I'll tell you why in a second. Does anybody have that? You should know it, but if you don't, do you know about what it is?
For pi over 2?
Mm-hmm.
1.57?
Yeah, it's about 1.57. Because we're supposed to draw a picture. Our picture is going to go from 0 to pi halves. Now, between 0 and pi over 2, the sine curve starts out at 0, 0, and it's supposed to end up here at 1. So it's the part of the curve that looks like this. Right? I mean, we recognize that if we kept going, it would come back down, right? On the right-hand side of this. But this is the part that goes from 0 to pi halves. And we know that pi halves is about 1.57, so what in the world is the 0.88, roughly? Nope, it's an x value. It's almost midpoint, yeah. It's somewhere between 0 and pi halves, and it's almost halfway, right? I mean, 0.88 is pretty close to half of 1.57. It's not exact, but we're talking somewhere between that's close to 1/2, about right here. So it looks to me on my picture that I'm talking about a point that's about right here. And I want to draw the lines in to convince you that maybe that seems reasonable. So the slope of the line that we originally are talking about now is this one. Let me try it one more time. That's not good. Maybe from this angle. Oh, no, that was pretty good. All right, there's the slope that's between 0 and pi halves. And if I've got the right location, this slope for this tangent line should be about the same. Okay, we're going to have to say that's pretty close. It's as close as I'm getting. This is the value that's the inverse cosine of 2 over pi, about 0.88. It's at this particular x value. My picture's not great, but you have the right idea that that would be roughly the location where the slope is actually matching the picture, matching the slope for the other part of the picture. Any questions on that one? Okay, let's take a look at another problem. We have 2 more theorems before we go into the last 2 problems. Depending on when you printed your notes out there, your theorems might actually supposed to say 8.2. The first one's 8.2, the second one's 8.3. Theorem 8.2 says if f is continuous and differentiable, okay, so same conditions as before, the first 2. Also, we know that f of x equals 0 has 2 solutions between a and b. What does f of x equals 0 mean? Well, what does it mean for f of x to equal 0? Yes, that's a y value, right? F of x is just another way of writing y. So think about a graph. On a graph, where does y equal 0? Close. X-axis, x-intercepts. Yeah. So this is saying that if we have 2 x-intercepts, that somewhere between those 2 x-intercepts, we've also got the ability to have a slope of 0. And so take a picture in your mind, or I'll draw you one even, of what's going on here. This is saying that if we have a graph that looks like this, and we have two locations, or we have two x-intercepts, somewhere between them I've got a slope of 0. And this is obviously a pretty convincing graph, because I drew it on purpose to convince you, right? But even if we didn't have a parabola, which is an awfully friendly graph, it would still work. So let me draw you something that's maybe a little bit more interesting. You notice the phrase here says at least one, right? What if the graph did this? How many x-intercepts do you see? There are 3, right? And in particular, if we looked at the 2 on the outer edges, because it says it has 2 solutions. Well, here are 2 of the solutions, right? We could actually have 2 locations. But what's even more interesting is that what if the graph did this? Let me draw you one more graph. This one really just has the 2 solutions, right? Oops, move that around. 2 solutions right here, but how many places do you see on this one where the slope's 0? 3. So that phrase at least one really means at least one. It's not just sort of in there to sort of, cover our tail in case we sort of got it wrong. There are places and there are cases where if I have the 2 x-intercepts, I actually end up with really more than one solution. I could really end up with more than one. That would be a distinct possibility. This one had 3. Theorem 8.3 is a generalization of this theorem. Okay, so we've got an integer that's positive. We have this continuous and differentiable. And instead of it saying f of x equals 0 has 2 solutions, it says it has n solutions. Okay, so it hits the x-axis several times. 2 times, 3 times, 6 times, 12 times, I don't know. But then it will have at least n minus 1 solutions if it hits the graph n times. So if it hits the graph 5 times, right, if it hits the x-axis 5 times, you will at least have 4 solutions for the derivative equation. At least. You could have more, but at least 4. Okay, so let me show you how we can use this information to talk about a graph. And one of the things that's really tricky is to understand that the information you see on your calculator is always limited, right? When you look at a graph on the calculator, you are limited to the viewing window you're looking in. And you have no way to look at the entire spectrum of the entire viewing window because there isn't an entire viewing window. In theory, it goes on forever, right? So that's part of what we're going to see happen on the next equation, or next problem. This says to prove that this has exactly 2 solutions. Now, there's a word in here that should bother you based on the information we just saw on the previous screens. What word would that be? Exactly. The words that were used in the previous screen said at least, didn't they? And this one actually sort of caps it. Like I told you, we had 6 x-intercepts, we'd have at least 5 solutions. But we might have 7 or 12, right? We don't know. And this one says exactly 2. Okay, so that's limiting us. And so we're going to have to sort of come to an agreement of how to deal with that. The first thing I'd like for you to do is grab your calculator. I'd like for you to graph this function. And while you're graphing that, we're going to make sure that the first 2 conditions are all okay. The first 2 conditions had to do with it being continuous and differentiable. And again, we almost get those for free here. Why? Yeah, it's a polynomial. And because I'm mean, I want you to write that down every time you're doing these problems. Because if it failed to do this, you might be looking for something that doesn't exist. It's important. You don't want to go looking for something that doesn't exist. All right, so what does this graph more or less look like? It's not this, but it looks kind of like a what? Looks like a parabola. How many x-intercepts does it appear to have? 2. And where does it appear that the y-intercept is? Negative something, right? Okay, it's actually at -1. The basic graph looks something like this. Does that look good to you guys? I know not all of you have a calculator with you, Brooks doesn't, but it seems reasonable with the equation. We've got that intercept at -1. All right, so the first thing that we need to talk about is the picture looks like we have at least 2 solutions, right? I mean, we can't see the whole picture. What happens further out, we don't exactly know. We could zoom out on our calculator, but only to a certain degree anyway. So what do? Well, it looks like it has two solutions. We can verify that it has at least two solutions real quick, and that's where we're going to start. So the intermediate value theorem, do you guys remember that one? Intermediate value theorem was a theorem that told us that if you have a y value that's above the x-axis and another point where the y value is below the x-axis and it's continuous between them, somewhere it crossed the y-axis. Okay, I said wrong, x-axis, somewhere it crossed the x-axis. It was above the x-axis and below the, I used the word y, I'm sorry guys. If you have a point where it's above the x-axis and you have another location for a point on the curve that's below the x-axis, somewhere between them it crosses the x-axis. So if you take a look at these, you can kind of picture some points that you might want to choose. You're choosing points that are sort of around here. We're going to pick a point that we think is above the x-axis over here and below down here. And then we can use that same location here for the below here, and then pick another point above over here. So let's use points 1 and 0. Is that okay with you? I think it will work. Let's try using the point at point 1. So let's, well, negative 1 I mean, since we're on the left-hand side. What is f of negative 1 in this equation? Close. Oh, no, it is 6 because the one at the beginning. You're right. Yep, so this is 6. Sorry, thank you. Yes. 6. It's positive, right? So, I mean, we looked at we roughly found like this point. It's above the x-axis. Let's do f of 0. What happens when we do f of 0? We get negative 1. So this piece right here, by the intermediate value theorem, the graph has an x-intercept between negative 1 and 0. Somewhere between negative 1 and 0, it crosses the x-axis. And if we test the point at f of 1, what do we get?
6.
Yeah, we do. You're right. It's another 6. So this number is right here, the fact that we were at negative 1, which is below the x-axis, and then we're at positive 6, which is above the x-axis, tells us again that somewhere between those points we had to cross the x-axis. So I'm just going to add this in as another interval down here. We also have an x-intercept between 0 and 1. So we have at least 2 answers, right? We have at least 2 solutions. What we want to do is we want to say, yeah, but we know we don't have 3. How in the world can we say that we don't have 3? It's the interval from x equals 0 to x equal 1. It's not an ordered pair. These are intervals. I know that doesn't look very good because we use that notation both ways. But these are intervals from negative 1 to 0 and an interval from 0 to 1. And somewhere in between each of those intervals, we have an x-intercept. Okay, so let me show you what this tells us and how we can use these theorems to help us out. We're going to assume, for the moment, that we don't just have 2. We know we have at least 2. Agreed? Definitely have at least 2 solutions. Let's say for a moment that we say, okay, well, let's pretend we have 3. We're assuming that we have. So if we assume we have 3 solutions, we'll say suppose.
Is this the same problem?
Same problem. Mm-hmm. We have 3 solutions. Because see, so far all we've done in terms of the directions is we've shown that we have at least 2. We need to show exactly 2, which means we show that it's at least 2 and it can't be more. We showed that it was at least 2, we need to show that it can't be more. So we're saying let it be more. Let's say there's 3 of them. And we're going to run into a problem. So suppose we have 3 solutions to our equation. And if you'll remember from algebra, we actually have the potential to have 4 solutions to this equation. Do you know why? Because the highest degree is 4. So there actually, and to be honest, there are 4 solutions. They just may not all be in the real number system. Some of them may be imaginary numbers. Okay, so there are 4 solutions, but what we want to do is we want to show that there's only 2 of them that are the real number solutions. So we're pretending for the moment that we have 3 of them, and we're going to run into a contradiction. So suppose we have 3 solutions to our equation. Then, by theorem 8.7, what did I call it? 3. 8.3, the equation f prime of x equals 0 will have what? At least 2, right? Solutions. Okay, so let me go back over here. I know you guys want to write that down, but let me just show you where I'm getting these pieces of information. Theorem 8.3 says that if our original equation has 3 solutions, then the derivative will have at least 2. Okay, that's what I'm writing down. I'm using that theorem to write that statement down. So what we want to do then is to take the derivative and see how many solutions the derivative actually has. All right, so the derivative then. This is another very exciting derivative. What is the derivative for the function? In fact, let me write down the original function. X to the 4th plus 6x squared minus 1. What is the derivative? And what we want to do is we just want to set this equal to 0 and solve it. All right? So how do we solve 4x cubed plus 12x? Good. Can we factor out a 4 too, Zach?
Yeah, that's what I was.
Good, yeah. It wouldn't matter if we didn't, but we might as well since we're factoring anyway. What would I be left with if I factor out a 4x? Excellent. All right, so this is factored form. Now what? Mm-hmm. All right, so this is good news on the first one. 4x equals 0 means x equals 0. How about x squared plus 3 equals 0? What happens on that one? What do you get? Somebody's saying square root. Is it? Okay, we got a plus or minus, and we've got a square root of what? Negative 3. What's the square root of negative 3? It's imaginary. And calculus that we're working with is not in the imaginary number system. Okay? We're only working in the real number system in Calculus 1. So this right here is an imaginary or a non-real solution. So how many solutions did we get? 1. So f prime of x equals 0 has only 1 solution. So f of x cannot have 3 solutions. Because if it did have 3 solutions, we should have gotten 2 solutions at least when we did the derivative down here. And we didn't. Hence, f of x has 2 solutions. Only 2. We showed before it had at least 2, right? Intermediate value theorem. And then we have to show it can't have more. It can't have 3. So we assumed it did have 3, and we run into a contradiction. The contradiction was that when we assumed that we had 3 solutions, we should have gotten 2 solutions from the derivative set equal to 0, and we didn't. So we ran into this problem.